Okay, the next presentation actually is a pre-recorded one. Presenters couldn't attend due to visa issues. So I will introduce the speaker, Chunshu Gu. Dr. Gu received his PhD in computer engineering from Boston University, where his research focused on architecture design on FPGAs. Then he pursued postdoctoral research in the Department of Electrical and Computer Engineering at the University of Rochester, specializing in dynamical system-based AI hardware co-design. He will soon join Pacific Northwestern National Lab and continue this area of research.
Hello, everyone. I'm Chunshu Wu, a postdoc from University of Rochester, supervised by Professor Tong. There are three key elements in the title I will talk about today: dynamical system, on-device lifelong learning, and nonlinear node interaction. Before showing the contributions of our work, let's first look at the general motivation. The figure shows from year 2010 to now, 2025, the computing demand for AI training is increased by more than 10 orders of magnitude, from 10 to the 14th to 10 to the 26th in flops. Well, in the meantime, the computing capabilities of supercomputers also increase, but only for 3 orders of magnitude in the 15 years. So if we use a supercomputer on the right for a training task on the left, it would take minutes in 2010, but it takes years for models in 2025. And this causes a big gap in training time, about 1 million times. Thanks to the efforts in architectural optimization, data format, etc., this gap is still manageable, but observing this trend of this gap, we intend to walk along an orthogonal path to explore the possibilities of new computing powers. In terms of the alternative computing powers, there's quantum computing, there's photonic computing. In addition to those, there's electronic dynamical system. Let's make a brief comparison between electronic dynamical system and these two before. In terms of speed, the electronic dynamical system is not necessarily the fastest. As quantum computers, they specialize in specific tasks through quantum effects such as quantum tunneling, while photonic computers, they perform computation at the speed of light. And in terms of power, although the electronic dynamical system is typically lower in power than quantum computing considerably, some photonic computers, they can achieve picowatt level power. Well, however, on all 3 other aspects, cost, scalability, and design flexibility, electronic dynamical systems typically prevail because of the mature CMOS manufacturing technology. With that being said, a natural question is, what does the dynamical system do? Or what exactly is the dynamical system? Let's look at an example. This video shows the process of water turning into ice, a process where water molecules spontaneously find the lowest energy state of the entire system. An electronic dynamical system also chases the lowest energy state, like the animation shows. We call it natural annealing. Like the water system, the electronic dynamical system is also massively parallel, and it evolves at electron speed with electrons. However, unlike most natural systems, an electronic dynamical system can be designed, meaning that the equation of evolution can be controlled for specific tasks. Actually, the variable sigma in the electronic dynamical system can be modeled as voltages, and the energy gradients can be modeled as electric currents. The relation shows how currents change the voltages, just like charging capacitors. Consequently, the spontaneous energy decrease described in the relation in the formula is translated to natural capacitor charging process. At equilibrium, the variables correspond to the lowest energy state, and the process of reaching this equilibrium is as the animation shows. Another natural question is, how do we use this to solve real-world problems? A previous work showed that this system can be used for graph learning. In this work, there are 3 steps. Step 1 is to design the energy function. Step 2 is to perform training, mapping data to energy minimum. And step 3 is to perform natural annealing and get inference results. Well, however, 2 critical problems exist. The first is that in this work, the variables only have linear interaction, and the expressivity of this model is highly limited. The second problem is that training relies on expensive offline processing. It's not directly compatible to this electronic dynamical system. These 2 problems correspond to our key contributions. Our first contribution is to propose a nonlinear extension method to this system. In fact, real-world graphs typically have nonlinear relations among variables. For example, in a traffic graph, a row segment may influence another in a very complex way. We realize that a nonlinear function can be expanded into series. For example, the Taylor series are used to approximate a function near a point. So similarly, the relation between, for example, sigma I and sigma j, the 2 variables, can be extended accordingly. The hat above sigma I means it is an estimated value from the model. Well, however, there are some constraints that apply. The first is that each term in a series must have an upper bound and a lower bound to satisfy physical limitation of voltages. And the second is that for each term, it should not be oscillating too much. So probably polynomials are better than the Fourier series. And finally, our choice is to use the Chebyshev polynomials for their bounded and slow varying features. As you can see, for x between -1 and 1, each term is also limited in that range, satisfying the physical constraints. Let's first look at the original architecture for linear interactions. A node in a graph is influenced by other nodes, and this process is modeled as a node value in the design influenced by electric currents. The electric currents are produced from coupling units that connect the other nodes. For example, a node sigma j as voltage, it passes through a MOSFET as a variable resistor in the coupling unit to produce current that influences node sigma I. To perform nonlinear extension, we use a nonlinear generator to produce separate terms and embed the coefficient for each term into a coupling unit. Eventually combine the influences for all the Chebyshev polynomial terms as a summation. The nonlinearity generator with the first 3 polynomial orders are shown in the figure below, where the sigma j signal can be efficiently reused. Now let's talk about the solution to the second problem. During the study of dynamical system, we realized that human brain is also a dynamical system. There's knowledge stored in human brain, and there's also new observations. When the observation does not match the knowledge, a human can compare the differences and update the knowledge to match the observation. This process may continue in a human's lifetime. Therefore, we have the inspiration number 1. Can we use an electronic dynamical system to mimic the brain behavior? Additionally, we are inspired by a concept called mortal computation proposed by Hinton. And we summarize 2 key points from his work. The first point is that training and inference should be on the same device. And second, by doing this, significantly lower cost is expected. So the task becomes updating the resistor-based knowledge with voltage-based observations. To compare the knowledge and observation, we need to model them as unified physical quantities in a dynamical system. In particular, we modeled the observation as electric current IR, reflecting the influence of observation to the system. We modeled knowledge as electric current IN, which is obtained from coupling units where parameters are stored. We further modeled the knowledge gap as I loss, which refers to the difference between the two currents, IN and IR. So as long as there is discrepancy between observation and knowledge, the I loss is non-zero. Let's look at the corresponding architecture. The figure shows the interaction from node J to node I. IN is driven by the coupling unit that contains knowledge, while IR is driven by the voltage in node I showing observation. The current feedback unit is also detailed to the right, but this module is disabled during inference. To have a brief recap, the inference mechanism is illustrated as the electrons propagate in the system. The electric current IN charges the capacitor in node I, which in turn affects the value of IR. At equilibrium, IN equals to IR. For a well-trained model, the voltage on the capacitor in node I is the truth or the observation. Now let's look at on-device training. During training, the voltage in node I and the voltage in node J are fixed to observations. Therefore, current I of R is determined by the observation in node I. Let's say IN is now greater than IR, and the discrepancy I loss is non-zero. The I loss signal then goes through the current feedback unit to charge the capacitor in the coupling unit. This effectively modifies the resistance or the value of Jij. As the parameter gets modified, the corresponding IN current is modified too. In other words, we are dragging equilibrium to the observed ground truth. Just like the animation shows, through on-device training, this energy landscape is learned, mapping the observation with equilibrium. Theoretically, we first write the MIC loss in the form of I loss. Then we derive the gradient using I loss. And finally, we obtain the parameter update rule, which satisfies the dynamical system's continuous time requirement. Let's combine nonlinear extension and on-device learning and see what the architecture is like. A node is equipped with nonlinearity generator for a nonlinear extension. It is also equipped with an I loss current path for current feedback in on-device training. The nodes interact through spin interaction modules, where the spin is just another name for variable. Each spin interaction module contains M current feedback modules and coupling units based on the number of Chebyshev polynomial terms M. To summarize the contributions, we developed the current-based on-device learning and the nonlinear interaction mechanisms, as well as their corresponding architectures, aiming to solve real-world graph learning problems. The results show that after nonlinear extension, the accuracy is improved over 6 different datasets compared to our predecessor DSGL that uses linear node interactions and compared to state-of-the-art GNNs. Here, DS-TPU best refers to the best result up to the third order of Chebyshev polynomials. And further experimental results show that, unlike offline learning approaches for electronic dynamical systems, our approach is robust against mismatch due to the capability of on-device learning. In terms of latency, we observed that despite using the third-order Chebyshev polynomials, the training speedup is more than 2 orders of magnitude compared to state-of-the-art GNNs and offline training on an A100 GPU. For fair comparison with the state-of-the-art GNN accelerators, their utilizations are assumed to be 100%. Yet we still achieve more than 2 orders of magnitude speed up in inference and over 3 orders of magnitude in energy saving. Thank you for listening, and I'm open to questions.